Means we're going to start with a function that is already composed, and we want to figure out, can we determine what were the original pieces, what were the original two functions that we have put together. So determining originals from composition, we're going back, we're breaking it down. So rather than putting it together, we're decomposing it. Decomposition. So if we have a function h that represents a composition, can we go back and determine what the original f and g were? So here are three examples of composed functions. We want to be able to go backwards and decompose them. So if we look at h here, what is a function that we see? Perhaps two functions that we see. I see a square root sign, which represents one function, and I also see a linear. There's 3x minus 2 represents a linear function on the inside. So if we let g of x represent the linear function, the inside bit, then we could write it like this: square root of 3x minus 2, and therefore this radical is going to be represented by f. So the two functions were a square root function and a linear function. And what we saw in this h of x was f of g of x, where we put g inside of the square root. So this will require some visual manipulation and maybe some creative problem solving. So looking at the next one, look at this h. This is a quadratic. I see something squared, and I see something, and I also notice that the two brackets are the same piece. So again, let's have the inside function be that bracket, right? Which means if I look at just the bracket pieces, right? I'll just put that here. If this represents G, then what's on the outside of the brackets must represent F. F would look like x squared plus 3x plus 4, right? So again, looking at h and looking at f, if I substitute those x's with this linear function, I do end up with the h, the composed function. So that's what the two functions must be. I must have a regular quadratic, 3x plus 4 here, and I must have a linear function, x minus 4, because if I put this in here, I end up with that, which is what I want. Okay, this one, not as easy to see. There's no brackets here and there's no obvious function. It's just a quadratic. So the strategy here is to factor. You can use magic numbers or you can use your powers of observations. I notice that this is a perfect square and this is a perfect square and this is 2 times 3, which means this is the perfect square of x minus 3. If you're not sure how I did that, you can use magic numbers for this one. Okay, but factored form, here we are. This is h of x, the composed function. Well, now I have a bracket, and now I can see some things. I see a linear function on the inside, and I see a quadratic on the outside. And there's just a lot of words here that I don't need to do, but let's skip some steps here. Looking at the inside, the g function, let's use the linear as that representation, and the x function is the quadratic. Okay, so we have a linear inside of a quadratic. That is how I got that composition, right? So this is f of g of x. So f is something squared, g is the linear. There we go. So we ended up with what we started. All right, so that's decomposition, is really just looking at the equations, seeing if we can break it down and pull apart what is the inside function, what is the outside function. If you understand composition, I'm hoping decomposition is a bit easier to understand because it's more of a visual manipulation and doesn't require too much brain work. Working with examples of applications, this is just word problems, right? Word problems where we're looking at two things that are dependent on, for example, time, I guess in this case, and you want to find one thing in terms of the other. So let's do this example, and we'll call it a day for our lesson today. The temperature as you descend a mine shaft is a function of the depth below the surface. An equation expressing the relationship is capital T equals 0.01 D plus 20, where capital T is the temperature and D is the depth. Note that the temperature is in degrees Celsius. Your first planning and subway, so grade 9, could you please just gotta wait for the announcements. All right, so if you go down a mine shaft at a rate of 4 meters per second, this is speed, right? Express the temperature as a function of time in T seconds. And then in B, it's asking us what is the temperature after 1 minute of travel. Okay, since the rate of travel, meaning our speed is 4 meters per second, the distance in meters traveled in T seconds will be determined how. I don't remember if you guys did this in Science 9 or 10, but it's called the DTS triangle. DTS, distance, time, and speed. And so if you want distance, you multiply the bottom two. If you want time, time is distance divided by speed. And if you want speed, it is distance divided by time. So the DTS triangle is very, very useful in this case. Right now, we are needing distance and we are given speed. So I use the DTS triangle and say, okay, if I want distance, then this is speed times time. Okay, so this will be speed times time. We know what our speed is, so this is going to be 4t, where t is in seconds. Really important there. T is in seconds. So this is a composition. The temperature depends on distance, but distance depends on time. So I'm going to substitute my distance equation for t, which makes this 0.04 t plus 20 as my composition equation. Okay, in part B, it's asking us, what is the temperature after 1 minute of travel? Now remember, our equation is based on seconds. So first thing we got to do is, what is 1 minute of travel in seconds? Hopefully we know this without too much thinking. 60 seconds. So I go to my temperature equation, I substitute 60, and now I got to grab a calculator. Oh, I could probably do this in my head, but let's not and say we did. 0.4 times 60 is 2.4 plus 20, which is going to be 22.4, and this is degrees Celsius. That is my final answer. All right. In class tomorrow, we are going to work on some check your understanding. I would encourage you to try some of these questions ahead of time, though. All right. Have a good day, everyone.